Tonight, we're going to explore something that sits at the very edge of what physics can explain. Right now, everything in the universe, every interaction, every push, every pull, every force you've ever felt or will ever feel is supposed to come from just four fundamental forces. Four. That's it. Four forces to explain everything from the light on your screen to the gravity holding you in your chair to the nuclear reactions powering the sun. But here's the problem. There are things happening in the universe that those four forces can't fully account for. Measurements that don't add up. Experiments that give answers nobody expected. And physicists have been quietly asking a dangerous question. What if there's a fifth force? One we haven't found yet, one that changes everything. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that sounds almost too simple to be true. Everything you have ever experienced, every sensation, every event, every interaction between every object in the entire observable universe, all of it comes down to just four forces. Four. Not 40, not 400, four. That's the number of fundamental forces that physics has identified after centuries of careful experimentation, brilliant theoretical work, and painstaking measurement. Four forces that together explain why apples fall from trees, why the sun shines, why atoms exist, why magnets stick to your refrigerator, why your body holds together instead of dissolving into a cloud of subatomic particles. Everything. Every single physical interaction you can name traces back to one of these four forces. And the fact that the number is so small, that such an enormous range of phenomena can be explained by such a tiny set of underlying interactions, is one of the most remarkable discoveries in the history of human thought. It suggests that beneath all the apparent complexity of the universe, there is a deep and elegant simplicity. A set of rules so compact you could write them on a napkin, yet so powerful they govern the behavior of everything from the smallest particle to the largest galaxy cluster. That's not just impressive, that's breathtaking. And understanding these four forces is essential before we can even begin to ask whether something might be missing. So let's go through them, one by one, because each of these forces has its own character, its own personality, its own domain, and together they paint a picture of reality that is both stunningly complete and, as we'll see later, strangely incomplete. The first force, and the one most familiar to you, is gravity. You've lived with gravity every moment of your life. It's the reason you stay on the ground. It's the reason rain falls. It's the reason the Earth orbits the sun, and the moon orbits the Earth. Gravity is the force that acts between anything with mass or energy, pulling it toward anything else with mass or energy. Every object in the universe that has mass exerts a gravitational pull on every other object. You're pulling on the Earth right now, and the Earth is pulling on you. The sun is pulling on Jupiter, and Jupiter is pulling on the sun. A grain of sand on a beach in Australia is gravitationally pulling on a mountain in Norway. These forces are tiny at small scales, but they're always there, always present, always reaching. Isaac Newton was the first to describe gravity mathematically in 1687. His law of universal gravitation said that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This equation was revolutionary. It explained the motion of the planets. It explained why objects fall at the same rate, regardless of their mass. It predicted the existence of Neptune before anyone ever saw it, simply by observing the wobble in Uranus's orbit. Newton's gravity was one of the greatest achievements in human intellectual history. But Newton's description wasn't the final word. In 1915, Albert Einstein published his general theory of relativity, which replaced Newton's idea of gravity as a force pulling objects together with something far stranger. Einstein showed that gravity is not really a force at all in the traditional sense. It's the curvature of space-time. Massive objects bend the fabric of space and time around them, and other objects moving through that curved space-time follow paths that look like they're being pulled by a force, but they're actually just following the natural contours of bent space. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet bends around the ball. If you roll a marble across the sheet, it curves toward the bowling ball. Not because the bowling ball is pulling it, but because the sheet itself is curved. That's essentially what gravity is, according to Einstein. Mass tells space-time how to curve, and curved space-time tells objects how to move. Einstein's theory has been tested extensively for over a century, and it has passed every single test. It predicted the bending of light around massive objects, which was confirmed during a solar eclipse in 1919. It predicted gravitational time dilation, the slowing of time in strong gravitational fields, which has been confirmed using atomic clocks on airplanes and satellites. GPS systems have to account for this effect. Without corrections for general relativity, GPS would drift by several kilometers within a single day. In 2015, the LIGO experiment detected gravitational waves, ripples in the fabric of space-time caused by two black holes merging over 1 billion light years away. Einstein predicted these waves a century earlier, and it took that long for our technology to become sensitive enough to detect them. Gravity is by far the weakest of the four fundamental forces. That might surprise you because gravity seems pretty powerful when you're falling off a ladder or watching a massive star collapse into a black hole. But compared to the other three forces, gravity is extraordinarily weak. Here's a simple demonstration. Take a small refrigerator magnet and stick it to your refrigerator. That tiny magnet is holding itself up against the gravitational pull of the entire planet Earth. The electromagnetic force in that small magnet is overpowering the gravity of a 6 trillion kilogram planet. That's how weak gravity is compared to electromagnetism. The difference in strength is staggering. Electromagnetism is roughly 10 to the 36 power times stronger than gravity. That's a 1 followed by 36 zeros. It's not even close, yet despite being so weak, gravity dominates on the largest scales. It shapes galaxies, holds solar systems together, governs the motion of galaxy clusters, and determines the large-scale structure of the entire universe. The reason is that gravity has two unique properties that the other forces don't share. First, it's always attractive. There's no such thing as negative mass or anti-gravity in any confirmed observation. Every mass pulls on every other mass. This means gravity accumulates. The more mass you gather, the stronger the pull, and the more mass you attract, creating a runaway effect. Second, gravity has infinite range. It gets weaker with distance, but it never fully disappears. The gravitational influence of a star reaches across the entire observable universe, getting weaker and weaker, but never hitting zero. These two properties, always attractive and infinite range, mean that on cosmic scales where you're dealing with enormous amounts of mass spread, across vast distances, gravity wins. The other forces either cancel out over large distances or don't reach far enough, but gravity just keeps pulling relentlessly across the entire cosmos. The second fundamental force is electromagnetism. This is the force responsible for light, electricity, magnetism, chemistry, and essentially every interaction you experience in daily life that isn't gravity. When you touch a table and feel its solidity, that's electromagnetism. The electrons in the atoms of your hand are repelling the electrons in the atoms of the table. When you see color, that's electromagnetic radiation of different wavelengths entering your eye. When you feel warmth from a fire, that's infrared electromagnetic radiation hitting your skin. Your entire nervous system runs on electrical impulses. Every chemical bond in your body, every molecule, every protein, every strand of DNA, all of it is held together by electromagnetic interactions between charged particles. Electromagnetism was unified into a single force in the 1860s by James Clerk Maxwell. Before Maxwell, electricity and magnetism were thought to be separate phenomena. People knew about static electricity, they knew about magnets, but they didn't realize these were two aspects of the same underlying force. Maxwell showed that electric fields and magnetic fields are intimately connected. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. And these oscillating fields can propagate through space as waves. Electromagnetic waves. Maxwell calculated the speed of these waves and found it matched the measured speed of light. Light itself, he realized, is an electromagnetic wave. This was one of the greatest unifications in physics. In one stroke, Maxwell had shown that electricity, magnetism, and light were all manifestations of a single force. Electromagnetism is carried by a particle called the photon. Every electromagnetic interaction, from the light leaving your lamp to the force between two magnets to the chemical bonds holding water molecules, together involves the exchange of photons between charged particles. Photons are massless, which is why electromagnetic forces have infinite range, just like gravity. And photons travel at the speed of light, which makes sense because they are light. The photon was one of the first force-carrying particles to be understood, and it remains the most familiar. Every time you see anything, you're detecting photons that have traveled from some source, bounced off objects in your environment, and entered your eye. Electromagnetism is enormously stronger than gravity at small scales. It's what gives atoms their structure, binding electrons to nuclei. It's what holds molecules together. It's what gives materials their properties, from the hardness of diamond to the conductivity of copper to the transparency of glass. Virtually every technology humans have ever built exploits electromagnetism in some way. Computers, phones, motors, generators, lasers, radios, medical imaging, all electromagnetic. Now we come to the two nuclear forces, and this is where things get less intuitive because these forces operate on scales far smaller than anything you can directly perceive. They're confined to the atomic nucleus, a region so small that it takes about 100,000 nuclei laid side by side to span the width of a single atom. And yet, without these forces, atoms could not exist, stars could not shine, and the universe would be a fundamentally different place. The third fundamental force is the strong nuclear force, sometimes just called the strong force. This is the most powerful force in the universe. If electromagnetism is 10 to the 36th power times stronger than gravity, the strong force is about 100 times stronger still than electromagnetism at nuclear distances. It's the titan among forces, and its job is simple but critical. It holds atomic nuclei together. Here's the problem it solves. An atomic nucleus contains protons and neutrons, packed incredibly tightly together. Protons are positively charged, and you know from electromagnetism that, like, charges repel each other. So all those protons crammed into a tiny nucleus should be violently pushing each other apart. The electromagnetic repulsion between protons in a nucleus is enormous. By all rights, every atomic nucleus heavier than hydrogen should instantly explode. But they don't. They hold together. The reason is the strong force. It provides an attractive force between protons and neutrons that is so powerful it overcomes the electromagnetic repulsion between the protons. It glues the nucleus together against tremendous electromagnetic opposition. The strong force is carried by particles called gluons, and it operates between quarks, the fundamental particles that make up protons and neutrons. Each proton contains 3 quarks, and each neutron contains 3 quarks. And gluons fly back and forth between these quarks, binding them together with extraordinary strength. The strong force has a peculiar property. Unlike gravity and electromagnetism, which get weaker as distance increases, the strong force actually gets stronger as you try to pull quarks apart. It's like a rubber band that gets stiffer the more you stretch it. If you try to separate 2 quarks, the energy required increases so rapidly that at some point it becomes more energetically favorable for new quarks to pop into existence from the vacuum than for the original quarks to be separated. This is why you never see a free quark floating around by itself. Quarks are permanently confined inside particles like protons and neutrons. This phenomenon is called confinement, and it's one of the most remarkable features of the strong force. But the strong force has a severe limitation. Its range is incredibly short, only about 1 femtometer, which is 1 quadrillionth of a meter. That's roughly the diameter of a proton. Beyond this distance, the strong force drops to essentially zero. This is why the strong force doesn't affect everyday life. It's immensely powerful, the most powerful force in existence, but it only operates over distances smaller than an atomic nucleus. A millimeter away, it might as well not exist. The fourth and final known fundamental force is the weak nuclear force, often just called the weak force. Despite its name, it's not actually the weakest force. That title belongs to gravity. The weak force is about 10 to the 25th power times stronger than gravity. But it's weaker than both electromagnetism and the strong force at nuclear distances, which is where it gets its name. The weak force is responsible for certain types of radioactive decay. Specifically, it governs processes in which one type of particle transforms into another type. The most common example is beta decay, where a neutron inside a nucleus transforms into a proton, releasing an electron and an antineutrino in the process. This might sound like an obscure process, but it's incredibly important. Beta decay is one of the key reactions that powers the sun. Inside the sun's core, hydrogen nuclei are being fused into helium through a chain of reactions, and several steps in that chain rely on the weak force to convert protons into neutrons, or vice versa. Without the weak force, the sun wouldn't shine, stars wouldn't burn, the universe would be a cold, dark place. The weak force is carried by 3 particles: the W plus boson, the W minus boson, and the Z boson. These are heavy particles, much heavier than protons. The W bosons have a mass of about 85 times the proton's mass, and the Z boson is about 97 times the proton's mass. Because these carrier particles are so massive, the weak force has an extremely short range, even shorter than the strong force. Its effective range is only about 1,000th of a femtometer, roughly 1,000th the diameter of a proton. This makes it incredibly local. It only operates in the most intimate subatomic interactions. In the 1960s and 70s, physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg achieved something remarkable. They showed that the electromagnetic force and the weak force are actually two aspects of a single unified force, called the electroweak force. At very high energies, the kind that existed in the first fraction of a second after the Big Bang, electromagnetism and the weak force behave as one. They become indistinguishable. But as the universe cooled, a process called symmetry breaking caused this unified force to split into the two separate forces we observe today. The photon remained massless, giving electromagnetism its infinite range, while the W and Z bosons acquired their enormous masses, restricting the weak force to its tiny domain. This unification was confirmed experimentally in 1983 at CERN when the W and Z bosons were discovered, exactly as the theory predicted. It was a triumph of theoretical physics, and it raised an obvious question. If two of the four forces are really one force in disguise, could all four forces be unified? Could there be a single underlying force from which all four emerge? Physicists have been working on this question for decades. Some progress has been made in unifying the electroweak force with the strong force in what are called grand unified theories, but none of these theories has been experimentally confirmed. And unifying gravity with the other three forces has proven extraordinarily difficult. This is one of the great unsolved problems in physics, and we'll come back to it later. These four forces, gravity, electromagnetism, the strong force, and the weak force, are described by our two most successful theories of physics. The standard model of particle physics describes three of them: electromagnetism, the strong force, and the weak force. General relativity describes gravity. Together, these two frameworks account for virtually every physical phenomenon we've ever measured. The standard model has been tested to extraordinary precision. Some of its predictions match experimental measurements to 10 or 12 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. General relativity has been confirmed by every experiment designed to test it for over a century. These are not tentative hypotheses. They are the most rigorously tested and precisely confirmed theories in the history of science. Every force you experience in daily life, friction, tension, air resistance, the normal force that keeps you from falling through your chair, all of these are ultimately electromagnetic in origin. They're the result of electromagnetic interactions between atoms and molecules at the surface of objects. When you push a door open, the force you feel is electromagnetic. When wind blows against your face, that's electromagnetic. When a spring pushes back against your hand, electromagnetic. The strong and weak forces operate only inside atomic nuclei, and gravity operates between masses across all distances. But the rich variety of everyday forces are all just electromagnetism wearing different costumes. The framework is beautiful in its economy. Four forces, a handful of equations, and they describe everything from the behavior of subatomic particles to the large-scale structure of the cosmos. You can use these forces to predict how a ball rolls down a hill, how a satellite orbits the Earth, how a star forms from a collapsing cloud of gas, how a supernova explodes, how atoms form in the aftermath, how those atoms combine into molecules, how those molecules form planets, and how on at least one of those planets, chemistry became biology and biology became consciousness. The chain of causation from the Big Bang to you sitting here listening to these words is governed at every step by these four forces. That's the power of this framework. It's not just a description. It's a complete account of physical reality as we understand it. The Standard Model also identifies the particles that make up all known matter. Quarks come in 6 types, called flavors: up, down, charm, strange, top, and bottom. Leptons also come in 6 types: the electron, the muon, the tau, and their corresponding neutrinos. These 12 matter particles, along with the force-carrying bosons, the photon for electromagnetism, the gluons for the strong force, the W and Z bosons for the weak force, and the Higgs boson, which gives mass to the W and Z bosons and other fundamental particles. These together form the complete cast of characters in the Standard Model. Every atom in your body is made of up quarks and down quarks bound together by gluons into protons and neutrons, with electrons bound to those nuclei by photons. That's it. That's what you're made of at the most fundamental level. Quarks, electrons, gluons, and photons. 4 types of particles interacting through 4 forces building everything. The Higgs boson, discovered at CERN in 2012, was the final piece of the Standard Model puzzle. Its discovery confirmed the existence of the Higgs field, which permeates all of space. Particles that interact with this field acquire mass. Particles that don't, like the photon, remain massless. The discovery of the Higgs was a monumental achievement. It confirmed a prediction made nearly 5 decades earlier and completed a theoretical framework that had been under construction since the 1960s. For a brief moment, it seemed like physics might be finished. Like we had identified all the fundamental pieces of reality, all 4 forces, all the matter particles, all the force carriers, the picture was complete. But it wasn't complete. Not really. Because even as physicists celebrated the discovery of the Higgs boson, they knew there were problems. Serious problems. Not small discrepancies or minor unexplained details, but fundamental gaps in our understanding. Observations that the 4 known forces simply cannot explain. Measurements that don't fit the Standard Model no matter how you twist and adjust it. And a persistent, stubborn inability to bring gravity into the same framework as the other 3 forces. The 4 forces we've described tonight are extraordinary. They represent one of humanity's greatest intellectual achievements, but they may not be the complete story, because the universe has features that these 4 forces, powerful as they are, cannot account for. And the next portion of this journey will take us into those cracks, into the places where the framework breaks down, into the anomalies that keep physicists awake at night, the places where reality doesn't quite match what our best theories predict. Because it's in those cracks, in those unexplained gaps, that the possibility of something new begins to emerge. Something beyond the 4 forces. Something we haven't found yet. Something that, if it exists, would fundamentally reshape our understanding of everything we thought we knew about how the universe works. So we've established the picture. 4 fundamental forces. A beautifully constructed theoretical framework. The Standard Model of particle physics, describing 3 of those forces with extraordinary precision, and general relativity describing gravity with equal success. Together, these 2 theories account for virtually every measurement physicists have ever made. They predicted the existence of particles before those particles were discovered. They predicted the behavior of light, matter, and energy across scales ranging from the subatomic to the cosmic. They work. They work spectacularly well. And yet, there are cracks. Not small ones. Not trivial inconsistencies that might be smoothed over with a minor adjustment or a better calculation. These are deep, structural fractures in our understanding of reality. Places where the universe does something that our best theories cannot explain. Places where careful, repeated measurements give answers that don't match what the four known forces predict. And these cracks have been widening for decades. The most dramatic of these cracks involves something that makes up most of the matter in the universe. Something we can detect through its gravitational effects, but cannot see, cannot touch, and cannot explain with any of the four known forces acting on any of the known particles. It's called dark matter, and it represents one of the most profound mysteries in all of science. The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies about 320 million light years from Earth. He measured how fast the galaxies within the cluster were moving by analyzing the light they emitted. When light from an object moving toward you gets compressed into shorter wavelengths, and light from an object moving away gets stretched into longer wavelengths, you can use this shift to calculate the object's speed. Zwicky measured the speeds of galaxies in the Coma Cluster and found something disturbing. They were moving far too fast. Here's the problem. A galaxy cluster is held together by gravity. The galaxies orbit within the cluster, bound by the gravitational pull of all the matter in the cluster. If you know how much matter is in the cluster, you can calculate how fast the galaxies should be moving. Zwicky did this calculation. He added up all the visible matter in the Coma Cluster, all the stars in all the galaxies, all the gas he could detect, everything he could see. And then he compared the gravitational pull of that visible matter to the speeds of the galaxies. The numbers didn't match. The galaxies were moving so fast that the gravity of the visible matter shouldn't be able to hold the cluster together. The cluster should have flown apart long ago. The galaxies should have escaped the cluster's gravitational grip and scattered into intergalactic space billions of years ago. But the cluster was clearly intact. It had been intact for billions of years. Something was holding it together. Something Zwicky couldn't see. Zwicky proposed that there must be invisible matter in the cluster, matter that doesn't emit or absorb light, but does exert gravitational force. He called it dark matter. At the time, most astronomers dismissed the idea. The measurements were crude, the analysis was rough. Maybe Zwicky had made a mistake. Maybe there was hot gas between the galaxies that he hadn't accounted for. The scientific community largely ignored Zwicky's dark matter proposal for decades. Then, in the 1970s, an American astronomer named Vera Rubin found the same problem, but this time within individual galaxies. Rubin was studying the rotation of spiral galaxies. In a spiral galaxy, stars orbit the galactic center, just like planets orbit the sun. You can even measure how fast stars at different distances from the center are orbiting by looking at the shifts in their light. According to Newton's laws and the known effects of gravity, stars far from the center of a galaxy should orbit more slowly than stars closer in, just as Neptune orbits the sun more slowly than Mercury does. The farther out you go, the less mass is inside your orbit, so the weaker the gravitational pull and the slower you should be moving. But that's not what Rubin found. When she measured the rotation speeds of stars in spiral galaxies, she found that stars far from the galactic center were orbiting just as fast as stars much closer in. The rotation curves were flat. Instead of dropping off with distance, the orbital speed stayed constant far out into the outer reaches of the galaxy. This made no sense with the visible matter alone. There simply wasn't enough mass in the visible stars and gas to explain why those outer stars were moving so fast. They should have been flung out of the galaxy entirely. The implication was the same as Wiki's finding, but now far more precise and far harder to dismiss. There had to be enormous amounts of invisible matter in and around galaxies. Matter that doesn't interact with light in any way, doesn't emit photons, doesn't absorb photons, doesn't reflect photons, but does exert gravitational force. And there had to be a lot of it. The visible matter in a galaxy, all the stars and gas and dust you can see, accounts for only about 15% of the galaxy's total mass. The other 85% is dark matter, invisible, undetectable by any means other than its gravitational influence. This has been confirmed over and over again by independent observations. Gravitational lensing, the bending of light from distant galaxies by the gravity of intervening matter, shows that there's far more mass along the line of sight than can be accounted for by visible matter. The cosmic microwave background radiation, the afterglow of the Big Bang, has a pattern of tiny temperature fluctuations that can only be explained if the early universe contained roughly 5 times as much dark matter as normal matter. Computer simulations of how galaxies and large-scale structures form match observations only if dark matter is included. Without dark matter, the simulations produce a universe that looks nothing like ours. So dark matter is real. The evidence for it is overwhelming and comes from multiple independent lines of observation. But here's the critical point for our story. We have no idea what dark matter is. None of the known particles in the standard model can account for it. Neutrinos were once proposed as dark matter candidates, but they're too light and move too fast to clump together in the way dark matter must. Dark matter doesn't interact through electromagnetism, which is why it doesn't emit or absorb light. It doesn't seem to interact through the strong force either. The only force we know it responds to is gravity, and possibly the weak force, though even that isn't certain. This is a staggering gap in our understanding. 85% of all the matter in the universe is made of something we cannot identify. Something that doesn't fit into the standard model. Something that interacts with the universe through a mechanism we don't fully understand. When 85% of the matter in the cosmos is unexplained, that's not a minor crack in the framework. That's a chasm. But dark matter is only one of the cracks. There's another mystery that's arguably even more bizarre. It's called dark energy, and it makes up about 68% of the total energy content of the universe. In 1998, 2 independent teams of astronomers made a discovery that shocked the world of physics. They were studying distant Type 1a supernovae, exploding stars that serve as cosmic distance markers because they all have roughly the same intrinsic brightness. By measuring how bright these supernovae appeared from Earth and comparing that to how bright they should have been at their known distances, the astronomers could track how the expansion of the universe had changed over time. Everyone expected to find that the expansion was slowing down. After all, gravity pulls matter together. The mutual gravitational attraction of all the matter in the universe should be decelerating the expansion, like a ball thrown upward, gradually slowing as gravity pulls it back. But that's not what they found. The expansion of the universe isn't slowing down, it's speeding up. The universe is expanding faster and faster with every passing moment. Something is pushing the universe apart, overcoming the gravitational attraction of all the matter in it. Something is acting like a repulsive force on cosmic scales, causing space itself to stretch at an accelerating rate. This something was named dark energy, and it earned the leaders of both teams the Nobel Prize in Physics in 2011. Dark energy is deeply strange. It accounts for about 68% of the total energy content of the universe. Dark matter accounts for about 27%. And all the normal matter, everything described by the standard model, all the atoms and molecules and particles that make up stars and planets and people, accounts for only about 5%. Let that sink in. The four forces and all the particles we've identified describe only 5% of what the universe is made of. 95% of the universe consists of things we cannot explain with our current physics. Nobody knows what dark energy is. One possibility is that it's a property of space itself, that empty space has an inherent energy that causes it to expand. Einstein actually predicted something like this with his cosmological constant, a term he added to his equations of general relativity in 1917. Einstein later called the cosmological constant his greatest blunder because he introduced it for the wrong reasons. But it turns out something like it might be real, though its observed value is absurdly different from what quantum mechanics predicts. When physicists use quantum field theory to calculate the expected energy of empty space, they get a number that's roughly 10 to the 120th power times larger than what's observed. That's one followed by 120 zeros times too large. This is sometimes called the worst prediction in the history of physics. The mismatch between the theoretical and observed values of the cosmological constant is one of the most embarrassing and unresolved problems in all of theoretical physics. Now, let's turn to a problem that's closer to the subatomic scale, something that directly challenges the standard model and has generated tremendous excitement among particle physicists in recent years. It involves a particle called the muon. The muon is essentially a heavier version of the electron. It has the same electric charge as an electron, responds to the same forces, but is about 207 times more massive. Like all charged particles, the muon has a magnetic property called a magnetic moment. This is essentially a measure of how strongly the muon interacts with magnetic fields. The standard model predicts the muon's magnetic moment with extraordinary precision. It's one of those calculations where the theory is tested to many decimal places. But here's the thing. When physicists at the Brookhaven National Laboratory first measured the muon's magnetic moment with extreme precision in the early 2000s, and then again more recently at Fermilab starting in 2018, the measured value didn't quite match the standard model prediction. The discrepancy was small in absolute terms, but given the precision of both the calculation and the measurement, it was statistically significant. The muon was behaving as though something was tugging on it, some interaction that the standard model doesn't account for. Some additional force or particle that was slightly altering its magnetic properties. This measurement, known as the muon G-2 anomaly, has been one of the hottest topics in particle physics. If the discrepancy is real, if it's not a mistake in the calculation or the measurement, then it implies that there's something beyond the standard model interacting with the muon, possibly a new particle, possibly a new force, something that affects the muon's behavior in a way that the known forces cannot explain. Now, it's important to be careful here. The theoretical calculation of the muon's magnetic moment is incredibly complex. It involves contributions from all three forces in the standard model: electromagnetism, the strong force, and the weak force, and some of these contributions are very difficult to compute precisely. Different methods of calculating the strong force contribution give slightly different results. And depending on which method you use, the discrepancy between theory and experiment either persists or partially vanishes. This is still being actively debated. But the fact that there might be a discrepancy, that the muon might be telling us something about physics beyond the standard model, has kept physicists intensely focused on this measurement. There's another crack that strikes at the very foundation of our existence. It's called the matter-antimatter asymmetry problem, and it's one of the most fundamental unanswered questions in all of physics. For every type of particle in nature, there exists a corresponding antiparticle. The antiparticle has the same mass but opposite charge and certain other opposite quantum properties. The antiparticle of the electron is the positron. The antiparticle of the proton is the antiproton. When a particle meets its antiparticle, they annihilate each other, converting their combined mass into pure energy in the form of photons. According to the standard model, the Big Bang should have produced equal amounts of matter and antimatter. The laws of physics, as we understand them, treat matter and antimatter almost identically. Every process that creates a particle also creates its antiparticle. So, in the early universe, there should have been exactly as much antimatter as matter. And when the universe cooled enough for particles and antiparticles to start meeting each other, they should have annihilated completely. Every particle should have found its antiparticle, and the universe should have ended up as nothing but radiation. No matter, no atoms, no stars, no planets, no you, nothing. But that's obviously not what happened. The universe is full of matter. You're made of matter. The Earth is made of matter. Stars and galaxies are made of matter. Antimatter is extraordinarily rare in the observable universe. Somehow, in the first moments after the Big Bang, a slight excess of matter over antimatter was produced. For every billion antimatter particles, there were about 1,000,000,001 Hatter particles. That tiny excess, that one extra particle out of 1,000,000,000, survived the Great Annihilation. And everything in the universe today, every atom, every star, every living thing, is made from that tiny surplus. The standard model does contain mechanisms that can produce a slight preference for matter over antimatter. There's a phenomenon called CP violation, where certain processes involving the weak force behave slightly differently for particles and antiparticles. CP violation has been measured in experiments with particles called kaons and B mesons. But the amount of CP violation in the standard model is far too small to explain the observed excess of matter. It falls short by many orders of magnitude. Something else must have tipped the scales. Some additional mechanism, possibly involving a force or interaction not included in the standard model, must have generated the matter-antimatter asymmetry that allowed the universe to exist as we know it. This is not a minor puzzle. This is a question about why anything exists at all. Why is there something rather than nothing? The four known forces, as currently understood, cannot fully answer this question. They predict a universe of pure radiation, a cosmos without atoms, without structure, without life. The fact that we're here means something is missing from our understanding. There are other anomalies worth mentioning. Neutrinos, for instance, were originally predicted to be massless by the Standard Model. But experiments in the late 1990s and early 2000s showed that neutrinos do have mass, albeit incredibly small mass. This was confirmed by the discovery of neutrino oscillations, where neutrinos change from one type to another as they travel through space. Neutrino oscillations can only occur if neutrinos have different masses. The first definitive evidence came from the Super Kamiokande detector in Japan, a massive underground tank filled with 50,000 tons of ultra-pure water. In 1998, the Super Kamiokande collaboration showed that muon neutrinos produced by cosmic rays hitting the upper atmosphere were disappearing as they traveled through the Earth. They weren't vanishing, they were transforming into tall neutrinos, a process that's only possible if neutrinos have mass. 2 years later, the Sudbury Neutrino Observatory in Canada, a detector built 2 kilometers underground in a nickel mine, solved the decades-old solar neutrino problem by demonstrating that electron neutrinos produced in the sun's core were oscillating into other types during their journey to Earth. The leaders of both experiments shared the Nobel Prize in Physics in 2015. The Standard Model had to be extended to accommodate massive neutrinos, but the mechanism by which they acquire their mass is still not fully understood. And this is a genuinely strange puzzle because neutrino masses are bizarrely small. The heaviest neutrino is at least 1,000,000 times lighter than the electron, which is itself the lightest charged particle. The Higgs mechanism, which gives mass to the W and Z bosons and to charged fermions like electrons and quarks, doesn't naturally explain why neutrino masses should be so extraordinarily tiny compared to everything else. The most popular explanation involves a hypothetical mechanism called the seesaw mechanism, which requires the existence of extremely heavy neutrinos that have never been observed. These heavy neutrinos might interact through forces or processes not included in the Standard Model. It might involve new particles or even new interactions that we haven't identified. And then there's the deepest crack of all, the one that has tormented theoretical physicists for nearly a century. The incompatibility between general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time. It works beautifully on large scales, governing the motion of planets, stars, galaxies, and the expansion of the universe itself. Quantum mechanics describes the behavior of particles on the smallest scales. It governs atoms, electrons, photons, quarks, and all the subatomic processes that make up the microscopic world. Both theories are extraordinarily successful in their respective domains, but they're fundamentally incompatible. They use different mathematical languages, they make different assumptions about the nature of reality. And when you try to combine them, when you try to apply quantum mechanics to gravity, the equations break down. You get infinities, meaningless, nonsensical answers, predictions that a particle interacting gravitationally at very short distances should produce infinite energy, which is physically absurd. The other three forces don't have this problem. Electromagnetism, the strong force, and the weak force have all been successfully described in quantum terms. Each has its force-carrying particle, its boson. The photon, the gluons, the W and Z bosons. These quantum descriptions work perfectly. They're the basis of the Standard Model, and they produce predictions that match experiments to extraordinary precision, but gravity resists this treatment. There's no confirmed quantum theory of gravity. There's no experimentally verified graviton, the hypothetical particle that would carry the gravitational force in a quantum framework. String theory and loop quantum gravity are two of the most developed attempts to create a quantum theory of gravity, but neither has produced testable predictions that have been confirmed by experiment. After decades of work by some of the most brilliant minds in physics, gravity remains stubbornly outside the quantum framework. This matters because there are situations in the universe where both gravity and quantum mechanics are important at the same time. Inside black holes, where enormous amounts of mass are compressed into incredibly small spaces, at the moment of the Big Bang, when the entire observable universe was compressed into a region smaller than an atom. In these extreme conditions, you need both theories simultaneously, and they refuse to cooperate. We literally cannot describe what happens at the center of a black hole or at the very first instant of the Big Bang, because our two best theories of physics give contradictory answers when applied together. Some physicists believe that resolving this conflict might require new forces or interactions that we haven't yet discovered. If gravity behaves differently at very short distances than general relativity predicts, if there's an additional interaction that only becomes apparent at scales we haven't yet probed, that could be the key to unifying gravity with quantum mechanics. This is speculative, of course, but the mere fact that our two most successful theories are incompatible tells us that our picture of reality is incomplete. Something is missing. And whatever is missing might take the form of a new force. There are also observations at the cosmological scale that raise questions. The universe appears to be remarkably flat, meaning its overall geometry is very close to Euclidean. It's also remarkably uniform on the larger scales, with matter distributed almost evenly in all directions. These features are explained by cosmic inflation, a hypothetical period of extremely rapid expansion in the first tiny fraction of a second after the Big Bang. Inflation smoothed out any initial irregularities and flattened the geometry of space. But inflation itself requires a mechanism to drive it, typically a hypothetical scalar field called the inflaton. The nature of this field and the force associated with it are unknown. Some physicists have suggested that inflation might be connected to a new interaction, something distinct from the four known forces. Let me step back and summarize what we found. Dark matter makes up 85% of the matter in the universe and doesn't fit into the standard model. Dark energy makes up 68% of the universe's total energy and has no explanation in current physics. The muon's magnetic moment might not match standard model predictions. The matter-antimatter asymmetry that allowed the universe to exist cannot be fully explained by the known forces. And gravity refuses to be reconciled with quantum mechanics, despite a century of effort. These aren't minor problems. These are foundational gaps. They tell us that the four known forces, as extraordinary and successful as they are, do not provide a complete description of reality. Something is missing. Maybe it's a new particle. Maybe it's a modification to one of the existing forces. Or maybe, just maybe, it's an entirely new force. A fifth fundamental interaction that operates in ways we haven't yet detected, affecting phenomena we can observe but not yet explain. And that possibility, that question of whether there's a force beyond the known four, is exactly what physicists have been testing for decades. Not with speculation or hand-waving, but with some of the most precise and carefully designed experiments ever conducted. That's where we're going next. Into the laboratories and observatories where scientists have been hunting for a fifth force, looking for the faintest whisper of something new hiding in the data. Something that could fill the cracks and reshape everything we think we know about how the universe works. So the cracks are real. Dark matter that nobody can identify. Dark energy that nobody can explain. A muon that might not behave the way the standard model predicts. A matter-antimatter asymmetry that shouldn't have produced a universe full of stuff. And a fundamental incompatibility between the two greatest theories in physics. These aren't hypothetical problems. These are measured, observed, documented features of reality that the four known forces cannot fully account for. And they raise an obvious, almost unavoidable question. What if there's another force? What if the four we know about aren't the complete set? This question isn't new. Physicists have been asking it for decades, and they haven't just been asking it abstractly, sitting in armchairs and wondering. They've been testing it, designing experiments, building instruments of extraordinary sensitivity, pushing the boundaries of measurement to look for the faintest possible signal of something beyond the known four. The search for a fifth force is one of the longest running and most meticulous investigations in modern physics. And the story of that search is filled with moments of excitement, disappointment, controversy, and above all, an unwavering commitment to following the evidence wherever it leads. The modern search for a fifth force arguably begins in 1986 with a physicist named Ephraim Fischbach at Purdue University. Fischbach and his colleagues did something deceptively simple. They went back and reanalyzed data from a classic experiment that had been performed nearly a century earlier. The original experiment was conducted by the Hungarian physicist Loránd Eötvös beginning in the 1880s and continuing into the early 1900s. Eötvös was testing one of the most fundamental assumptions in physics, something called the equivalence principle. The equivalence principle, which is a cornerstone of Einstein's general theory of relativity, states that gravitational mass and inertial mass are identical. Gravitational mass is what determines how strongly an object is pulled by gravity. Inertial mass is what determines how much an object resists being accelerated. There's no obvious reason why these two properties should be the same. One is about how strongly you're attracted to other masses. The other is about how hard you are to push. But as far as every experiment has ever shown, they're exactly equal. A feather and a bowling ball, in the absence of air resistance, fall at exactly the same rate. This isn't because gravity pulls on them equally. It doesn't. Gravity pulls much harder on the bowling ball because it has more gravitational mass. But the bowling ball also has more inertial mass, which means it resists acceleration more. These two effects cancel out perfectly, producing identical acceleration. This perfect cancellation is the equivalence principle, and it's the foundation upon which general relativity is built. Eötvös tested this principle with remarkable precision using a device called a torsion balance. He suspended different materials from a thin wire and measured whether they experienced slightly different gravitational accelerations. If the equivalence principle were violated, if gravitational mass and inertial mass weren't perfectly identical, then different materials would fall at slightly different rates. Eötvös found no violation to the extraordinary precision of a few parts per billion. His experiment was considered one of the most precise null results in the history of physics. It confirmed the equivalence principle and, by extension, supported general relativity. But nearly a century later, Fischbach looked at the Eötvös data again with fresh eyes. And he noticed something subtle. When he examined the small residual differences in the measurements, differences so tiny they had been dismissed as experimental noise, he found a pattern. The residuals seemed to correlate with a property of the test materials called baryon number, which is essentially a count of the total number of protons and neutrons in the material. Materials with different baryon number per unit mass showed slightly different gravitational accelerations. The effect was tiny, buried in the noise, but Fischbach argued it was statistically significant. Fischbach proposed that this pattern could be explained by a fifth force. Specifically, he suggested a new interaction that depended on baryon number and had a range of about 100 to 1000 meters. This force would be much weaker than gravity at long distances, but could become significant over intermediate ranges. He called it a hypercharge force because it coupled to a quantity related to the hypercharge of particles, a quantum number used in particle physics. The idea was that this new force would slightly modify the effective gravitational acceleration experienced by different materials depending on their composition. It wouldn't replace gravity, it would add a small correction to it. A correction so tiny that it had been missed by every previous experiment, but that might be lurking in the ALPS data. The paper caused an enormous stir. A fifth force was an extraordinary claim. If confirmed, it would overturn one of the most fundamental assumptions in physics, the equivalence principle, and would require a revision of general relativity. It would mean that gravity, or at least the effective force we experience as gravity, isn't purely geometric. It would have a component that depends on composition, on what objects are made of, not just how much mass they have. Experimentalists around the world rushed to test the claim. Over the following years, dozens of experiments were designed and carried out to look for a composition-dependent force at the ranges Fischbach had proposed. Groups in Australia, the United States, Japan, and Europe built new torsion balancers, dropped different materials in vacuum chambers, measured gravitational acceleration on hillsides and near cliffs, and performed a bewildering variety of precision tests. Some early experiments seemed to support the idea. A group in Australia measuring gravitational acceleration down a mine shaft found a small anomaly consistent with a fifth force, but other experiments found nothing. The results were contradictory and inconsistent. By the early 1990s, the consensus had shifted against Fischbach's fifth force. The most precise experiments found no violation of the equivalence principle. The anomalies that had been reported turned out to be caused by systematic errors, things like variations in the density of the rock surrounding mine shafts, subtle effects from local geology, and imperfections in the experimental apparatus. The composition-dependent force that Fischbach had proposed simply wasn't there, at least not at the strength and range he had suggested. But here's the important thing. Even though Fischbach's specific proposal was ruled out, the search didn't stop. If anything, it intensified. Because the experiments designed to test his idea had pushed the precision of gravity measurements to unprecedented levels. And in doing so, they had opened up new territory. They showed physicists exactly how sensitive their instruments could be, and exactly how much room remained for a new force to hide. This is a crucial point about how science works. A wrong idea can still be enormously productive if it motivates better experiments. Fischbach's fifth force proposal, even though it wasn't confirmed, generated a wave of precision measurements that improved our understanding of gravity and set much tighter limits on what kinds of new forces could exist. Before Fischbach, The equivalence principle had been tested to a few parts per billion. After the wave of experiments his paper inspired, it had been tested to parts per trillion. The window for a fifth force had gotten much smaller, but it hadn't closed entirely. And the reason it hasn't closed is that gravity is still the least well tested of the four fundamental forces, especially at short distances. We've tested electromagnetism, the strong force and the weak force, with extraordinary precision using particle accelerators and other laboratory instruments. We've confirmed the standard model's predictions for these forces to 10 or 12 decimal places in some cases. But gravity is different. Gravity is so incredibly weak that measuring it with precision at laboratory scales is enormously difficult. The gravitational force between two objects you can hold in your hands is so tiny that it's easily overwhelmed by electromagnetic effects, seismic vibrations, thermal fluctuations, and other sources of noise. Newton's law of gravity, refined by Einstein's general relativity, tells us that gravitational attraction follows an inverse square law. If you double the distance between two objects, the gravitational force drops by a factor of 4. This has been tested and confirmed over distances ranging from the scale of the solar system down to about 1/10 of a millimeter. But below that scale, at distances shorter than 1/10 of a millimeter, we actually don't know for certain that gravity behaves as general relativity predicts. The measurements simply aren't precise enough. There could be deviations from the inverse square law at short distances, deviations that would indicate the existence of a new force operating over very small ranges. This is why physicists have invested enormous effort in testing gravity at short distances. But measuring gravity at submillimeter scales is fiendishly difficult. The problem is that gravity is absurdly weak. At the scale of a millimeter, the gravitational attraction between two small masses is billions of times weaker than the electromagnetic forces between the atoms on their surfaces. And at these scales, other unwanted forces crowd in and contaminate the measurement. The Casimir effect, a quantum mechanical phenomenon where vacuum fluctuations of the electromagnetic field produce a measurable attractive force between closely spaced surfaces, becomes significant at distances below a micrometer. Electrostatic forces from stray charges on the surfaces of the apparatus can easily overwhelm a gravitational signal. Thermal vibrations, seismic noise from passing trucks or distant earthquakes, even the gravitational influence of people walking nearby, all of these create disturbances that must be painstakingly isolated and subtracted. Measuring gravity at short distances isn't just a matter of building a more sensitive detector. It's a matter of eliminating every other force in the universe from your measurement so that only gravity remains. Experiments at the University of Washington, led by a group often called the E-Earth-Wash group, in a nod to the original Earth-verse experiments, have used incredibly sensitive torsion balances to measure gravitational forces at submillimeter scales. These devices can detect forces as small as a few trillionths of a Newton. The apparatus must be operated in vacuum chambers to eliminate air currents, placed on vibration-isolated platforms to suppress seismic noise, and shielded from electromagnetic interference with meticulous care. They've tested the inverse square law down to distances of about 50 micrometers, roughly the width of a human hair. So far, no deviations have been found. Gravity behaves exactly as general relativity predicts down to these scales, but smaller distances remain unexplored. If a new force exists with a range shorter than 50 micrometers, we wouldn't have seen it yet. Some theoretical models predict exactly this kind of short-range force. String theory, one of the leading candidates for a quantum theory of gravity, predicts the existence of extra spatial dimensions beyond the three we experience. If these extra dimensions exist and have the right properties, they could modify gravity at short distances, producing deviations from the inverse square law that might be detectable with sufficiently precise experiments. Other models predict new particles that could mediate short-range forces. These hypothetical particles go by various names: axions, dilatons, moduli, depending on the specific theory. The point is that well-motivated theoretical frameworks predict new forces at short distances, and experimentalists are actively looking for them. The search for a fifth force has also moved into an entirely different domain, the world of particle physics. Because if a new force exists, it should be carried by a new particle, just as the other forces are carried by their respective bosons. And new particles, if they exist, might be produced in high-energy collisions at particle accelerators or detected through their effects on known particles. One of the most widely discussed candidates is something called the dark photon. Ordinary electromagnetism is carried by the photon. A dark photon would be a hypothetical particle similar to the photon, but associated with a new force that acts primarily on dark matter. The idea is elegant. If dark matter consists of particles that interact through their own force, separate from the four we know, then that force would need a carrier. The dark photon would be that carrier. And if the dark photon has even a tiny connection to ordinary photons, which some theories predict, then it could occasionally interact with normal matter, producing effects we might detect in the laboratory. Experiments around the world have searched for dark photons. At the Thomas Jefferson National Accelerator Facility in Virginia, an experiment called APEX has looked for dark photons produced when high-energy electrons strike a target. At CERN in Geneva, the Na-62 and Na-64 experiments have searched for dark photons in the decays of known particles. In Mainz, Germany, the A1 experiment has looked for dark photons using electron scattering. In Japan, the Bell 2 experiment at the KEK laboratory has searched for dark photons in electron-positron collisions. So far, none of these experiments have found a dark photon, but they've placed increasingly tight constraints on its properties. If a dark photon exists, it must have certain characteristics. It must be within a specific range of masses. It must interact with normal matter below a certain strength. The experiments haven't found it, but they've told us where it isn't, narrowing the search space and guiding future experiments. Another candidate that has generated significant attention is called a protophobic boson. This is a hypothetical particle that interacts preferentially with neutrons rather than protons. Unlike a dark photon, which would be a modified version of the electromagnetic force carrier, a protophobic boson would represent a genuinely new kind of interaction, one that distinguishes between protons and neutrons in a way that none of the known forces do. The protophobic boson entered the spotlight because of a remarkable and controversial experiment conducted at the Institute for Nuclear Research in Debrecen, Hungary. This experiment, often called the Atomki experiment after the Hungarian name of the institute, has produced one of the most intriguing and debated results in the search for a fifth force. In 2015, a team led by physicist Attila Krasnohorke reported an anomaly in the decay of an excited state of beryllium-8. When they produced excited beryllium-8 nuclei and watched them decay, they observed the emission of electron-positron pairs. This is expected. What wasn't expected was the angular distribution of those pairs. Standard nuclear physics predicts that the number of electron-positron pairs should decrease smoothly as the angle between the electron and positron increases. But the Atomki team found a bump, an excess of pairs at a specific angle of about 140 degrees. This bump didn't match any prediction from the standard model. The team proposed that the bump could be explained by the creation and immediate decay of a new, previously unknown particle with a mass of about 17 million electron volts, roughly 33 times the mass of an electron. This hypothetical particle was dubbed X17. If real, it would be a boson, a force-carrying particle, and it would represent a new fundamental interaction. Theoretical physicist Jonathan Feng and his colleagues at the University of California, Irvine, analyzed the Atomki result and proposed that the X17 particle could be a protophobic boson, a carrier of a fifth force that couples primarily to neutrons. The Atomki result generated enormous excitement. A new particle at a mass of 17 million electron volts would be relatively easy to produce and study if it really existed. Numerous experiments around the world began planning searches for the X17. In 2019, the Atomki team reported observing a similar anomaly in the decay of excited helium-4 nuclei, with the bump consistent with the same 17 million electron volt particle. This second observation strengthened the case, because finding the same anomaly in two different nuclear systems is much harder to explain as an experimental error. But the result remains highly controversial. Other laboratories have not yet independently confirmed the anomaly. Several groups have attempted to reproduce the measurement with different experimental setups, and so far, the results have been inconclusive. Some physicists have raised concerns about possible systematic errors in the Atomki experiment, such as issues with the detector calibration, background subtraction, or the nuclear physics modeling used to predict the expected angular distributions. These are legitimate concerns. Extraordinary claims require extraordinary evidence, and a new fundamental force is about as extraordinary as claims get. Several experiments are now specifically designed to test the Atomki anomaly. The PADME experiment at the Frascati National Laboratory near Rome is searching for the X17 particle using positron beams. The Montreal experiment at McGill University is using nuclear reactions to look for the same anomaly in independent conditions. The MEG2 experiment at the Paul Scherrer Institute in Switzerland, while primarily searching for a different kind of new physics, has sensitivity to particles in the mass range of the X17. If these experiments confirm the Atomki result, it would be one of the most revolutionary discoveries in the history of physics. A confirmed fifth force, carried by a new particle, interacting with matter in a way that none of the known forces do. It would open an entirely new chapter in our understanding of the universe. But if they don't confirm it, if the anomaly turns out to be an artifact of the experimental setup, then the X17 will join a long list of tantalizing hints that ultimately didn't pan out. And that list is long. The history of the search for a fifth force is littered with false alarms. This isn't a criticism of the scientists involved. It's a reflection of how difficult this search is. You're looking for something extraordinarily subtle, a force so weak or so short-ranged that it has escaped detection despite a century of increasingly precise measurements. Any signal is going to be small, right at the edge of what instruments can detect. And at the edge of detection, noise can look like signal. Systematic errors can masquerade as new physics. Statistical fluctuations can create patterns that seem meaningful, but aren't. One famous example occurred in 2015 when physicists at the Large Hadron Collider at CERN observed an unexpected bump in their data at an energy of about 750 billion electron volts. The bump appeared in the diphoton channel, meaning pairs of high-energy photons were being produced at a rate slightly higher than the standard model predicted. For months, the physics community was electrified. Hundreds of theoretical papers were written proposing explanations for the bump. Could it be a new particle, a new force carrier, a doorway to physics beyond the standard model? By the following year, after more data had been collected, the bump had vanished. It was a statistical fluctuation, nothing more. The signal had been noise all along. This pattern repeats itself over and over in experimental physics. A tantalizing hint appears. Theorists rush to explain it. Experimentalists collect more data. The hint disappears. It's frustrating, but it's also how science is supposed to work. You test, you measure, you follow the evidence, and sometimes the evidence leads to a dead end. That doesn't mean the search was wasted. Every null result, every experiment that finds nothing, tells us something important. It tells us where the fifth force isn't. It narrows the possibilities. It sets tighter constraints on what a new force could look like if it exists. Let's talk about what a fifth force would actually need to look like to be consistent with everything we already know. Because the constraints are severe. We've tested the 4 known forces with extraordinary precision. Any new force has to be consistent with all those existing measurements. It can't contradict things we've already confirmed. First, a fifth force would need to be either very weak or very short-ranged, or both. If it was strong and long-ranged, we would have detected it already. The precision of our measurements of gravity, electromagnetism, and the nuclear forces places strict limits on how strong a new force can be at any given range. At distances larger than about a millimeter, any new force must be far weaker than gravity, which is already the weakest known force. At shorter distances, a new force could potentially be stronger, but experiments are rapidly closing that window as well. Second, a fifth force would need its own carrier particle, its own boson. This is a requirement of quantum field theory, the mathematical framework that describes all known forces at the quantum level. The photon carries electromagnetism. Gluons carry the strong force. The W and Z bosons carry the weak force. A fifth force would need its own boson. The properties of this boson, its mass, its spin, its coupling to matter, would determine the character of the force. A very heavy boson would produce a very short-range force. A massless boson would produce a force with infinite range. The X17 particle proposed by the Atomki group would be a relatively light boson, giving a force with a range of about 12 femtometers, roughly the size of a large atomic nucleus. Third, a fifth force would need to interact with matter in a way that's consistent with all existing measurements. This is perhaps the tightest constraint. We've measured the properties of known particles, electrons, muons, quarks, neutrinos, with extraordinary precision. Any new force that acts on these particles would slightly alter their measured properties. The fact that our measurements match the standard model's predictions so closely means that any new force must interact with known particles very weakly. It can't significantly change the predictions we've already confirmed. This is why the protophobic boson idea is so interesting, theoretically. By coupling primarily to neutrons rather than protons, it would avoid many of the constraints from experiments that involve electromagnetic interactions, which are primarily sensitive to charged particles like protons and electrons. A force that acts mainly on neutrons would be invisible to many of the most precise tests of the standard model. It would hide in a blind spot of our experimental apparatus, which is exactly the kind of place a new force would need to hide to have escaped detection so far. Fourth, a fifth force might interact with dark matter. In fact, this is one of the most theoretically motivated possibilities. If dark matter consists of particles that don't interact through electromagnetism or the strong force, as the evidence suggests, then how do dark matter particles interact with each other? Gravity alone might not be enough to explain the behavior of dark matter in all observed situations. Some observations of galaxy clusters suggest that dark matter particles might have some small self interaction, bumping into each other at low rates. If so, this interaction might be mediated by a new force, a dark force carried by a dark boson. The search for a fifth force is not one experiment. It's an entire field of research spanning multiple disciplines. Particle physicists search for new bosons at accelerators. Gravitational physicists test the inverse square law at short distances. Nuclear physicists look for anomalies in nuclear decays. Astrophysicists analyze the behavior of dark matter in galaxies and galaxy clusters. Cosmologists study the cosmic microwave background for signatures of new interactions in the early universe. Each of these approaches probes a different aspect of the question. Each is sensitive to different types of new forces, and collectively, they're squeezing the space where a fifth force could hide, making the constraints tighter and the remaining possibilities more specific. As of now, no fifth force has been confirmed. Let me be absolutely clear about that. Despite decades of searching, despite hundreds of experiments, despite numerous tantalizing hints and anomalies, there is no confirmed observation of a fundamental force beyond the four we know. Every proposed signal has either been refuted by subsequent measurements, remains unconfirmed by independent experiments, or is still too ambiguous to constitute definitive evidence. The four forces we started this journey with, gravity, electromagnetism, the strong force, and the weak force, remain the only confirmed fundamental interactions in physics. But the search continues. It continues because the cracks in our framework are real. It continues because dark matter demands an explanation. It continues because the muon might be telling us something we don't yet understand. It continues because the matter in the universe shouldn't exist according to our current theories. And it continues because the history of physics has shown, again and again, that what we think is the complete picture almost never is. In the early 1800s, people knew about gravity and electrostatics and magnetism. That was the complete picture. Then Maxwell unified electricity and magnetism, and we learned about electromagnetic waves. In the early 1900s, people thought they understood matter and energy. Then quantum mechanics revealed an entirely new world of subatomic behavior that nobody had imagined. In the 1930s, the strong and weak nuclear forces were discovered, forces that had no analog in everyday experience, forces that operated on scales too small to perceive directly. Each time physicists thought they had the complete list of nature's forces, nature revealed something new. Maybe the list is complete now. Maybe four forces really are all there is. That's a genuine possibility, and it would be foolish to dismiss it. But the weight of the unsolved problems, the sheer volume of unexplained observations, the persistent failure to unify gravity with the other three forces, all of these suggest that the story isn't over, that there might be chapters yet to be written, forces yet to be discovered, particles yet to be found. And that's what makes this search so compelling. It's not just an academic exercise in pushing the precision of measurements one decimal place further. It's a search for something fundamental about the nature of reality, something that could change how we understand the universe at its deepest level. If a fifth force exists, finding it would be one of the most important discoveries in the history of science. And if it doesn't exist, proving that conclusively would be almost equally important, because it would force us to find other explanations for the anomalies that currently haunt our best theories. The experiments are running, the data is being collected, the analysis is being done with extraordinary care and rigor. Somewhere in the noise, hidden, beneath layers of known physics and experimental uncertainty, there might be a signal, a faint whisper of something new. Something that doesn't fit the standard model. Something that can't be explained by gravity or electromagnetism or the strong force or the weak force. Something that, if confirmed, would add a fifth entry to the list of nature's fundamental interactions and open an entirely new chapter in humanity's understanding of the universe. Or there might be nothing. The noise might be just noise. The anomalies might resolve themselves as better calculations and measurements converge. The four forces might truly be everything. And the problems that haunt physics today might be solved not by a fifth force, but by something else entirely. Something even stranger. Something we haven't thought of yet. Either way, the search itself is one of the most remarkable endeavors in human history. A species of apes on a small planet orbiting an ordinary star, building instruments of mind-boggling precision to probe the deeper structure of reality, looking for forces that are too weak or too subtle for any human sense to perceive, looking for the invisible threads that might connect the things we can see to the vast majority of the universe that we can't. That's what the search for a fifth force is, and it's far from over. So, where does all of this leave us? We've walked through the four known forces that govern every interaction in the observable universe. We've explored the cracks in that framework, the deep and persistent anomalies that the known forces cannot explain. We've followed the decades-long experimental search for a fifth force, from Fischbach's reanalysis of century-old data to the controversial Atomki anomaly, and the worldwide hunt for dark photons and protophobic bosons. And we've arrived at a clear but unsatisfying conclusion. No fifth force has been confirmed. The four forces we start with remain the only verified fundamental interactions in physics, and yet the problems that motivated the search haven't gone away. They're still there, still unexplained, still demanding answers. Now let's step back and think about what this all means. Not just for physicists working in laboratories, but for our understanding of reality itself. Because the search for a fifth force isn't really about adding one more entry to a list. It's about something much deeper. It's about whether we truly understand the rules that govern the universe. It's about whether the framework we've spent centuries building is the final framework, or whether there's something beyond it, something we haven't grasped yet, something that, once understood, might reshape everything we think we know. Let's start with dark matter, because this is the problem that most directly connects to the possibility of a fifth force. We know dark matter exists. The evidence is overwhelming and comes from multiple independent sources: galaxy rotation curves, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, computer simulations that match observations only when dark matter is included. All of these tell the same story. There is roughly 5 times as much dark matter as normal matter in the universe, and it interacts gravitationally but not electromagnetically. It doesn't emit light, it doesn't absorb light, it doesn't scatter light. It's invisible to every telescope and detector designed to observe electromagnetic radiation. But what is it? After decades of searching, we still don't know. The leading candidates fall into two broad categories. The first is weakly interacting massive particles, or WIMPs. These are hypothetical particles that interact through gravity and possibly through the weak nuclear force, but not through electromagnetism or the strong force. WIMPs have been the most popular dark matter candidate for over 30 years because they arise naturally in several extensions of the standard model, particularly in a framework called supersymmetry. The idea is elegant. If the early universe contained heavy particles that interact only weakly with normal matter, then as the universe cooled, these particles would have frozen out of the cosmic soup at just the right density to account for the observed amount of dark matter. This coincidence, sometimes called the WIMP miracle, made WIMPs the frontrunner for decades. Enormous experiments have been built to detect WIMPs. Deep underground laboratories, shielded from cosmic rays and other background radiation, house massive detectors made of ultra pure materials, liquid xenon, liquid argon, germanium crystals, all waiting for a WIMP to bump into a normal atom and produce a detectable signal. The xenon experiment in Italy, the LOX Zeppelin experiment in South Dakota, the Pandex experiment in China, these are among the most sensitive particle detectors ever constructed. They can detect the recoil of a single atom struck by a passing particle. And after years of operation, collecting enormous amounts of data with extraordinary sensitivity, they found nothing. No WIMPs, no signal at all. Just silence. This doesn't mean WIMPs don't exist. They could be lighter or heavier or more weakly interacting than the original predictions suggested. The experiments still have room to push further, but the simplest, most natural WIMP models have been largely ruled out. If WIMPs exist, they're hiding in corners of parameter space that are increasingly difficult to reach. And some physicists are starting to wonder whether the WIMP paradigm is the wrong approach entirely. This is where a fifth force becomes particularly relevant. If dark matter doesn't interact through the weak force, if it interacts only through gravity and some new force that we haven't discovered, then WIMP detectors would never see it. You'd be looking in the wrong place entirely. A new dark force, carried by a dark photon or some other new boson, could be the interaction that governs dark matter's behavior. Dark matter particles might interact with each other through this force, forming structures and dynamics in the dark sector that mirror the complexity of the visible world. There could be dark atoms, dark chemistry, even dark astrophysical objects, all governed by a force we haven't identified. This isn't pure speculation. Observations of galaxy clusters have provided hints that dark matter might have self-interactions. When galaxy clusters collide, the dark matter in each cluster passes through the other. By studying how the dark matter distributions overlap or separate during these collisions, astronomers can estimate how strongly dark matter particles interact with each other. The bullet cluster, observed in 2006, is the most famous example. Two galaxy clusters slammed into each other at tremendous speed. When astronomers mapped the aftermath, they found something remarkable. The hot gas in each cluster, which makes up most of the visible matter, had collided violently. The gas clouds smashed into each other and slowed down, piling up in the middle of the collision like two waves crashing together. But the dark matter in each cluster didn't slow down at all. Gravitational lensing maps showed that the dark matter had passed straight through, separating cleanly from the visible gas and continuing on its original path as though the other cluster's dark matter barely existed. This separation between visible and dark matter was dramatic and visually unmistakable. It became one of the strongest pieces of direct evidence that dark matter is real and not simply an artifact of our misunderstanding of gravity. But it also raised a question. The dark matter passed through almost unimpeded, which means its self-interaction must be very small. But some observations of other merging systems suggest that dark matter self-interactions are not exactly zero. If dark matter particles do interact with each other, even weakly, that interaction would need to be mediated by some force. And if it's not one of the four known forces, it would have to be something new. A fifth force operating primarily in the dark sector. Now, let's connect this to the matter-antimatter asymmetry problem. Remember, the standard model predicts that the Big Bang should have produced equal amounts of matter and antimatter. The small CP violation present in the weak force isn't sufficient to explain the observed excess of matter. Something additional must have tipped the balance. One possibility is that a new force or interaction was active in the early universe, one that violated the symmetry between matter and antimatter more strongly than the weak force does. This hypothetical interaction might have been significant only at the extremely high energies present in the first moments after the Big Bang, which is why we don't observe it today. But its effects would be permanent, baked into the composition of the universe, in every atom that exists. Several theoretical frameworks propose exactly this. Baryogenesis models, which attempt to explain the origin of the matter excess, often invoke new interactions beyond the standard model. Some of these models include new force-carrying particles that mediate interactions between quarks and leptons in ways that violate the symmetry between particles and antiparticles. If such a force exists, its carrier particle might be too heavy to produce in current particle accelerators, which would explain why we haven't seen it. But next generation accelerators, if they're built, might be able to reach the necessary energies. The muon G-2 anomaly also connects to this broader picture. If the muon's magnetic moment really does deviate from the standard model prediction, the most natural explanation would be that the muon is interacting with a particle or force not included in the standard model. This new interaction would contribute a small additional correction to the muon's magnetic properties, producing the observed discrepancy. The specific characteristics of the anomaly, its size and sign, can tell theorists what kind of new interaction might be responsible. Some models explain the anomaly with a new light boson, not unlike the X17 particle proposed by the Atomki group. Others invoke heavier particles associated with supersymmetry or other extensions of the standard model. The muon anomaly, if it holds up, could be the first direct experimental evidence of a new force acting on known particles. That would be transformative, but we need to be careful. As we discussed earlier, the theoretical calculation of the muon's magnetic moment is extraordinarily complex, and different methods of computing the strong force contribution give different results. What makes this particularly urgent right now is that the two main approaches, lattice quantum chromodynamics and data-driven methods using electron-positron collision measurements, are converging on different answers. Lattice calculations, which simulate the behavior of quarks and gluons directly on a computational grid, have recently suggested that the standard model prediction might actually be closer to the experimental measurement than the older data-driven approach indicated. If the lattice results hold up, the anomaly could shrink significantly or even disappear. But the data-driven method, which uses real experimental measurements of electron-positron collisions to estimate the strong force contribution, still points to a genuine discrepancy. Resolving which approach is correct is one of the most important open questions in particle physics right now. This is an active area of research. The muon G-2 experiment at Fermilab is continuing to collect data, improving the precision of the measurement. Theoretical groups around the world are refining their calculations. Within the next few years, we should have a much clearer picture of whether the anomaly is real or whether it was an artifact of imprecise theoretical calculations. If it's real, it's a smoking gun for new physics. If it goes away, the search for a fifth force loses one of its most promising leads, but the other motivations remain. Let's talk about the future of the experimental search, because the next decade promises to be one of the most exciting periods in the history of fundamental physics. Several experiments currently under construction or in the planning stages are specifically designed to test for new forces with unprecedented sensitivity. The MAGIS experiment, being developed at Stanford University and at Fermilab, uses atom interferometry to search for new forces. Atom interferometry is an extraordinarily precise technique that exploits the wave nature of atoms. Clouds of ultra-cold atoms are dropped in a long vertical shaft, and laser pulses split each atom's quantum wave function into two paths. The two paths travel slightly different routes through space, and then recombine, creating an interference pattern that's exquisitely sensitive to any forces acting on the atoms. MAGIS will be able to detect forces millions of times weaker than gravity at ranges from centimeters to kilometers. It's one of the most promising tools for detecting a fifth force at intermediate distances. In Europe, the CERN laboratory is exploring plans for a successor to the Large Hadron Collider. The proposed future circular collider would be a particle accelerator roughly 100 kilometers in circumference, nearly 4 times the size of the current LHC. It would reach collision energies far beyond what the LHC can achieve, opening up territory where new particles and new forces might be hiding. If a fifth force carrier exists, but is too heavy to be produced at the LHC, a more powerful machine might find it. The future circular collider is not yet approved, and its construction would take decades, but it represents the next major step in humanity's exploration of the subatomic world. The ALPS II experiment at the DSE laboratory in Hamburg, Germany, is searching for axions and other light particles that could mediate new forces. ALPS II uses a powerful laser shining through a strong magnetic field. If axions or similar particles exist, the magnetic field should convert a tiny fraction of the photons into these new particles, which could then pass through an opaque wall and be reconverted back into photons on the other side. It's a beautifully clever experiment, and it represents one of the most sensitive searches for new light bosons ever conducted. The axion itself, if discovered, would represent a new kind of particle associated with the strong force specifically a solution to a puzzle called the strong CP problem. But axion-like particles in general could mediate new forces, making experiments like ALPS II directly relevant to the fifth force question. Underground experiments are also pushing forward. The next generation of dark matter detectors, including Darwin, a proposed multi-ton liquid xenon experiment, will be sensitive enough to detect neutrinos scattering off nuclei. This is significant because neutrino scattering represents a fundamental background that previous experiments haven't reached. Once detectors are sensitive enough to see neutrino interactions, they're probing a regime where any new weak scale force should also produce a signal. If Darwin sees dark matter, it would narrow down the properties of whatever interaction connects the dark sector to the visible sector. If it sees only neutrinos and nothing else, it would push the dark matter interaction cross section below the neutrino floor, essentially closing the window for a large class of dark matter models and forcing physicists to consider alternative explanations, possibly including new forces with different characteristics. In astrophysics, observations of gravitational waves are opening a completely new window on the fundamental forces. The LIGO and Virgo detectors have already observed dozens of mergers between black holes and neutron stars. These events produce gravitational wave signals that carry information about the strong field behavior of gravity. If gravity deviates from general relativity in extreme conditions, if there's an additional component to the gravitational interaction that only becomes significant near black holes or neutron stars, then gravitational wave signals would show it. So far, every observed signal is consistent with general relativity, but as detectors improve and more events are observed, the precision of these tests will increase dramatically. The LISA mission, a space-based gravitational wave observatory planned for launch in the mid-2030s, will observe gravitational waves at much lower frequencies than ground-based detectors. LISA will be sensitive to the mergers of supermassive black holes, events involving masses millions or billions of times that of the Sun. These extreme events will test gravity in regimes we've never probed before. If a fifth force modifies gravity at these scales, LISA might see it. Let's think about what it would actually mean if a fifth force were confirmed. What would change? The answer is almost everything. First, it would shatter the framework that has dominated physics for half a century. The standard model, as successful as it is, would be revealed as incomplete in a very specific and dramatic way. Not just incomplete in the sense that it doesn't include gravity, which we already know, but incomplete in the sense that it's missing an entire fundamental interaction, an entirely new force of nature. That would be the most significant discovery in fundamental physics since the discovery of the weak nuclear force in the middle of the 20th century. Second, it could solve the dark matter problem. If the fifth force interacts with dark matter, it would provide a mechanism for detecting dark matter particles through the new interaction rather than through the weak force. This would transform dark matter research, opening up new experimental approaches and potentially allowing us to study the properties of dark matter in detail. We could learn what dark matter particles are, how massive they are, how they interact with each other and with normal matter. We could finally fill in the other 85% of the matter pie chart. Third, it could provide a bridge between quantum mechanics and gravity. One of the reasons gravity has been so resistant to quantization might be that we're missing a piece of the puzzle. If there's a fifth force that couples to gravity in some way, understanding it might reveal the missing link that allows us to construct a quantum theory of gravity. This would be one of the greatest achievements in the history of human thought, solving a problem that has resisted the efforts of the most brilliant physicists for nearly 100 years. Fourth, it could explain the matter-antimatter asymmetry. If the fifth force violates the symmetry between matter and antimatter more strongly than the weak force does, it could provide the mechanism that tipped the balance in the early universe, producing the slight excess of matter that allowed atoms and stars and planets and life to exist. It would answer one of the deepest questions in all of physics. Why is there something rather than nothing? Fifth, and perhaps most profoundly, it would change our philosophical understanding of reality. We would know that the universe is governed by at least 5 fundamental interactions, not 4. And if there are 5, could there be 6? 7? Could the number be much larger than we think? Every previous expansion of the list of forces, from gravity alone to gravity and electromagnetism, from 3 forces to 4 with the discovery of the weak force, has revealed entirely new aspects of reality that were previously hidden. A fifth force might do the same, opening doors we didn't even know existed. But we need to maintain perspective. As of today, no fifth force has been confirmed. Every anomaly that has been reported remains either unconfirmed, controversial, or potentially explainable within the existing framework. The Atomki anomaly is intriguing but not independently verified. The muon G-2 discrepancy might vanish as theoretical calculations improve. Dark matter might be explained by particles that interact only through gravity and the weak force without requiring any new interaction. The matter-antimatter asymmetry might be explained by mechanisms within extensions of the standard model that don't involve a new force. The incompatibility between quantum mechanics and gravity might be resolved through mathematical innovations rather than new physical interactions. This is the honest state of affairs. The search for a fifth force is motivated by real, deep, unsolved problems in physics. The experiments are well designed, rigorously executed, and increasingly precise. But the evidence for a fifth force remains circumstantial at best. What we have is not a discovery. It's a set of open questions that point toward the possibility of new physics without yet confirming it. And this is exactly how it should be. Science doesn't work by jumping to conclusions. It works by testing hypotheses with ever-increasing precision, following the evidence wherever it leads, and accepting the results even when they're not what you hoped for. The fact that we haven't found a fifth force yet doesn't mean the search was wasted. It means we've learned something important about the universe. We've learned that if a new force exists, it must be very weak or very short-ranged, or coupled to matter in very specific ways. We've narrowed the possibilities enormously. We've built instruments and techniques that push the boundaries of what's measurable, and we've set the stage for the next generation of experiments that will push even further. There's something deeply human about this search. For as long as our species has existed, we've looked at the world around us and asked why. Why do things fall? Why does the sun shine? Why do stars move across the sky? Every major advance in physics has come from someone noticing that the existing explanation wasn't quite right, that there was a crack in the framework, a measurement that didn't match, an observation that couldn't be explained. And every time, following that crack led to something extraordinary. Newton's gravity, Maxwell's electromagnetism, Einstein's relativity, quantum mechanics, the nuclear forces. Each one began as an anomaly, a discrepancy, a hint that something was missing. Today, we're in the same position. The anomalies are real. The cracks in the framework are genuine. Something about our understanding of the universe is incomplete. Whether that incompleteness takes the form of a fifth force or something else entirely remains to be seen. But the fact that we're looking, that we're building experiments to test the question with extraordinary precision, that we're willing to let the data guide us rather than our expectations. That's what makes science the most powerful tool humanity has ever developed for understanding reality. The universe doesn't owe us simplicity. It doesn't owe us elegance. It doesn't owe us a framework that fits neatly on a napkin with exactly four forces and nothing more. The universe is what it is, and our job is to figure out what that is, not to decide in advance what we think it should be. If there are four forces, the experiments will confirm that. If there are five or six, or something stranger than any number of forces, the experiments will reveal that too. But only if we keep looking. Only if we keep asking the question that has driven every great discovery in the history of physics. What if there's something more? Centuries ago, our ancestors looked up at the stars and thought they understood the heavens. They had a complete picture: the Earth at the center, the stars on a crystal sphere, the planets carried on nested rings. It was elegant, it was simple, and it was wrong. The universe was stranger and more magnificent than they imagined. Today, we look at the four fundamental forces and we might be making the same mistake. We might think our picture is complete when it isn't. We might be standing at the edge of a discovery that will transform our understanding of everything. A force that hides in the dark matter that holds galaxies together. A force that whispers in the anomalous spin of the muon. A force that tipped the balance between matter and antimatter in the first heartbeat of the cosmos. A force that bridges the gap between quantum mechanics and gravity, the two great pillars of physics that have stood apart for a century. Or maybe not. Maybe the four forces really are all there is, and the solutions to these mysteries lie somewhere we haven't thought to look yet. That's a perfectly valid possibility, and that's fine, because either way, the search teaches us something. It pushes the boundaries of what we know. It builds the tools we'll need for the next great discovery, whatever it turns out to be. The universe has been keeping its secrets for 13.8 billion years. It's been patient, and so must we be. Patient, but persistent. Patient, but curious. Patient, but never willing to stop asking the question that has driven every advance in human understanding. Since the first person looked up at the sky and wondered what was really going on. What if there's something we haven't found yet? What if there's a force we can't see? What if the universe has one more secret hidden in the spaces between what we know? That question, that simple, powerful, endlessly productive question, is the engine of everything we've discussed tonight. It's the reason Fischbach reanalyzed century-old data. It's the reason teams in Hungary fire protons at beryllium nuclei and watch what comes out. It's the reason physicists in South Dakota sit in underground laboratories waiting for a particle of dark matter to nudge a single atom of xenon. It's the reason engineers are designing the next generation of particle accelerators, gravitational wave detectors, and atom interferometers. It's the reason any of this matters. Because if we find it, if we discover that the universe is governed by 5 fundamental forces instead of 4, everything changes. Not just physics, not just our equations and our textbooks, our entire understanding of what the universe is, how it works, and what's possible within it. And if we don't find it, if we prove beyond doubt that four forces are truly all there are, then we'll have to confront an even more provocative question. If four forces are the complete set, why can't they explain everything we observe? What else are we missing? Either way, the search continues. The experiments are running. The data is flowing. And somewhere out there, in the gap between what we know and what we don't, the universe is waiting to be understood. It's been waiting for 13.8 billion years. And now, for the first time in all that time, there are minds capable of understanding the answer. Our minds, on this small planet, orbiting this ordinary star, inside this one galaxy among trillions. The four forces built everything we can see, but they might not be the whole story. And the search for the rest of that story, the search for the missing force that physics still can't explain, is one of the greatest adventures the human mind has ever undertaken. An adventure that's far from over. An adventure that might just change everything.